So I've enjoyed three major revolutions in Earth and planetary science over my career. One is the implications of the plate tectonic revolution. So plate tectonics uh, was sort of established a few years before I declared a geology major in 1972. So I wasn't there when this excitement happened, but it was still pretty exciting a few years later. The exploration of the solar system is a really remarkable thing that I was able to enjoy. It began in 1959 with the Soviet Union's Luna 1 to the moon, or maybe 1962 when NASA sent Mariner 1 to Venus. And we completed looking at all of the significant um, solar system bodies in 2015. And more than 30 bodies greater than 400 kilometers in diameter have been imaged. And then the third thing that was really exciting is the discovery and study of planets orbiting other stars in our galaxy. These are the exoplanets. First one was discovered in the 1990s, and now more than 4,000 are known. So this, our course focuses on one, but this lecture focuses on two, what we learned from the solar system. So, as we've got some planets in our solar system, all of them formed about the same time, 4.5 billion years ago. And there's a regularity to the planets, to their composition. The ones that are far from the sun are dominated by volatile elements like hydrogen and helium, very icy, cold, whereas planets close to the sun are rocky. So we could call them silicate planets. And we're interested in those because as geologists, we know something about the behavior of silicates, a number of things. So here we see the inner planets, the rocky planets. Here are the outer planets, the gassy and icy planets. Then there's kind of this asteroid belt in between. All right, so what I want to do here is go through a paper we wrote a few years ago we called it a tectonic manifesto. And we presented 15 concepts. So, there's tectonics is not just plate tectonics. For the purposes of this course, all tectonics is plate tectonics. But if we look around the solar system and almost certainly exoplanets, which we can't really see very well, the tectonics includes mostly not plate tectonics. So there's 15 concepts in here. All right, so here we've got the 30 of them, and the planets here are all in bold, and their diameters, their densities, which is uh, basically their mass over their volume. So we're quite comfortable on Earth. Our mean density is 5.5 grams per cubic centimeter. That's the core is much denser than the outer parts of the Earth. And the mass, whether or not these things are spherical, there's a few of them that aren't spherical, like Vesta and Proteus. These are small bodies that don't have enough gravity to pull themselves together. The likely composition of these bodies, here you see the silicates. Those are the ones we're interested in. These are interesting. These are of interest too. But these icy bodies we don't know much about. And then there's a thing called the TAI in here from 1 to 3, and we'll be talking more about that. And then over here is a list of the pertinent missions for imaging these. All right, so tectonic manifesto, concept number 1. Tectonics happen on silicate bodies, planets, moons, and perhaps exoplanets. So, 1, tectonics encompasses magmatic processes, thermal and deformational history, and the evolution of the lithosphere of planets and moons, where the lithosphere, which for the Earth includes the crust and upper part of the mantle, is the more rigid. So, 1, tectonics encompasses magmatic processes, thermal and deformational history, and the evolution of the lithosphere of planets and moons, where the lithosphere, which for the Earth includes the crust and upper part of the mantle, is the more rigid outer layer on top of less viscous ductile mantle, sometimes called a asthenosphere. Tectonics involves the entire lithosphere. So we'll be talking about all of that more in this class. Under this, we intentionally omit icy planets and satellites from consideration because they require separate treatment. These show ice tectonics, and what we're going to talk about really doesn't pertain to them. So, okay, this simply explains why we're focusing on these planets, because they're dense like the Earth, densities like the Earth, which implies similar compositions, and we're not doing these, the icy bodies. Okay? And now we're going to watch a video.
There is an expected difference between how this works out for planets forming in the inner parts of a solar system and how it works out for planets forming in the outer parts of the solar system. In the inner parts, closer to the central star, it's hot. At these temperatures, with no pressure, water molecules cannot take liquid or solid form. The solar wind from the forming star pushes these molecules along with helium and hydrogen molecules into the outer solar system. Planetesimals in this inner region wind up with little to no gas or water. That leaves metal and rock for these planets. In the outer parts, further from the central star, the water is frozen solid and therefore behaves like rocks. Planets out here have metal, rocks, and ice. This means that they're substantially more massive. This extra mass produces enough gravity to hold on to the gas as well. The dividing line is called the frost line or the snow line, and its distance from the star is temperature dependent. It will be located where the temperature falls to around 250 degrees Kelvin. That's minus 10 degrees Fahrenheit. The hotter the star, the further out this line will be. This explains the difference between the rocky planets in the inner solar system and the gas giant planets in the outer solar system. Our frost line is between 4 and 5 astronomical units. That puts it at the far rim of the asteroid belt.
How do we know whether a body is silicate, icy, or gassy? And density plays a big role. We'll talk about density a lot in this class. So here we have density. You've seen it as grams per cubic centimeter. Here it is in thousands of kilograms per cubic meter, from 0 to 6, and for the diameter of the bodies, right? So here are lots of low density icy things. And here are some big bodies that are also low density, but huge. And these things with a density of 3 or greater are very dominated by silicates. That certainly includes Earth and Venus, also Mercury, Mars as planets, but also the asteroid Vesta, the moon Io, the moon, our moon, and another moon of Jupiter's called Europa, which is covered in ice. We can't really study it. But these others we can study quite a bit. And this is very useful for understanding the range of tectonic activity that occurs on different silicate bodies. So we're going to focus on the silicate bodies in this class, in this lecture, and on Wednesday. So there's 7 silicate planetoids. I call them planetoids because they certainly include planets, but also moons. Io is a moon, and our moon is a moon, and then the asteroid Vesta is also a planetoid, even though it's very small. So we can talk about these in terms of being alive or dead. And this is in terms of tectonics. So here are the 4 living, which means tectonically active, silicate bodies of our solar system. Io is Jupiter's innermost moon. Venus, Earth, and Mars. Now here we see this TAI again. We mentioned the Tectonic Activity Index. Io has an activity index, a TAI of 3. Venus has an activity index of 3. Earth has a tectonic activity index of 3. Mars has a tectonic activity index of 2. We'll talk more about what that means. Here are the dead planetoids: Mercury, Moon, and Vesta. Mercury has a tectonic activity index of 1. The Moon has a tectonic activity index of 0. And Vesta has a tectonic activity index of 0. You'll notice that all of the active ones are big in terms of their diameters. Mars is the smallest. Well, actually, Io is the smallest, but we'll get Io's kind of an unusual situation. But Earth and Venus are huge with diameters of over 12,000 kilometers. These dead ones have diameters that are much smaller. So we're going to focus on the lessons from these. So all silicate planets or planetoids have a similar density structure: core, mantle, and crust. So there's here we see the core, the mantle, and the crust. So the core and the mantle and the crust may have different proportions. In general, the core and the mantle contain most of the mass of a body. The crust has a very small amount. I want to emphasize for the first time that there's a difference between composition and rheology. These differences in the density structure, crust, mantle, and core, those are compositionally distinct parts of the planet. This is different than rheologically distinct parts of the planet. And you may be confused. That's fine. We'll spend a lot of the time in this class explaining what we mean by rheology. In fact, we'll have a whole lecture on it. So, the rheologically distinct parts of the planet are not crust, mantle, and core. It is, from our point of view and our interest, lithosphere and asthenosphere. And understanding lithosphere and asthenosphere are keys to understanding planetary tectonics. All right, back to the Tectonic Manifesto. This is the concept 2. Lithosphere is where tectonics happens. Lithosphere is the relatively cool, strong, and rigid outer part of a silicate planet or moon, brittle at the top and ductile at the base. Heat flows through the lithosphere by conduction, in contrast to convection below it. In this sense, lithosphere is a thermal boundary layer. You haven't heard of the term thermal boundary layer before, but it's basically like, think of the blanket you slept under last night. That is a thermal boundary layer. It represents a huge step in the temperature of you at 98.6 degrees Fahrenheit and the air outside of you, maybe 60 or 70 degrees. So in that sense, it insulates you. So when you hear the word thermal boundary layer, think blanket. Some kinds of lithosphere exist on all but the hottest silicate bodies, and lithosphere is dominated by conductive heat flow. Again, lithosphere is where tectonics happens. All silicate planets and moons, whether they're tectonically alive or dead, have lithospheres after their early magma ocean stages. On active bodies, lithosphere overlies weaker and hotter mantle characterized by convective heat flow and adiabatic temperature gradients. We'll talk about what that means later. The point to be emphasized from this slide is lithosphere is the plate of plate tectonics. All silicate bodies have lithosphere, but only one has plate tectonics. Lithosphere includes the crust, but is mostly upper mantle. And we'll talk more about that too. So what is lithosphere? Again, lithosphere is the strong outer cold part of the planet. Heat flows through the lithosphere by conduction. It's the lid of single lid tectonics. That's a concept we haven't introduced yet, but will. And it's the plate of plate tectonics. And as we said before, lithosphere is composed of crust and uppermost mantle. Whereas asthenosphere is the weak, hot mantle beneath the lithosphere. Heat flow through the asthenosphere is controlled by convection. Asthenosphere is the source of mantle melt, which is basalt. Crust and mantle are compositional layers. Lithosphere and asthenosphere are rheological layers. Most geoscience students confuse crust and lithosphere. They are different. So I'll say many times in this class, if there's one thing I want you to get out of this class, it's this. And I'll have that for many things, but this is one of those things. If there's one thing I want you to get out of this class, I want you to understand the difference between the compositional layer crust and the rheological layer lithosphere. All right, let's watch a video.
This water boiling, the heat of the fire, and cooking on the skillet are all examples of heat transfer. In simple terms, heat is the transfer of energy from objects of different temperatures. As objects warm up or cool down, their kinetic energy changes. Kinetic energy is the energy of motion. Temperature is a measure of the average kinetic energy of the particles in an object. As temperature increases, the energy of motion increases. As the water warms up and the temperature increases, you can see an increase in the movement. Heat can be transferred in at least three ways: conduction, convection, and radiation. Conduction is a process in which the transfer of heat takes place between objects by direct contact. It is most often associated with solids. The key to conduction is direct contact. The heat of the pan is transferred to the mini pizzas. The energy of the frying pan is transferred to the eggs. Notice that they are in direct contact. Convection is heat transfer by the movement of a fluid such as air or water when the heated fluid is caused to move away from the source of heat, carrying the energy with it. This water boiling, the heat of the fire, and cooking on the skillet are all examples of heat transfer. In simple terms, heat is the transfer of energy from objects of different temperatures. As objects warm up or cool down, their kinetic energy changes. Kinetic energy is the energy of motion. Temperature is a measure of the average kinetic energy of the particles in an object. As temperature increases, the energy of motion increases. As the water warms up and the temperature increases, you can see an increase in the movement. Heat can be transferred in at least three ways: conduction, convection, and radiation. Conduction is a process in which the transfer of heat takes place between objects by direct contact. It is most often associated with solids. The key to conduction is direct contact. The heat of the pan is transferred to the mini pizzas. The energy of the frying pan is transferred to the eggs. Notice that they are in direct contact. Convection is heat transfer by the movement of a fluid such as air or water when the heated fluid is caused to move away from the source of heat, carrying the energy with it. It occurs due to density. Lava lamps are examples of convection. As the liquid is heated, it rises and falls as it heats and cools. As the paper burns, the air is heated up and begins to rise. The burning paper is swept up in the convection current, cools, and falls back down. These beans are another example of convection. As the beans warm up, they rise and then cool and fall back down, and repeat this over and over again. Radiation heat is transmitted without any physical contact between objects. Watch how the temperature of the lamp is transferred to the thermometer without touching it. These alligators and lizards use radiation from the sun to warm their bodies. If you'd like to know more about heat transfer and conduction, convection, and radiation, this playlist will help. And as always, thanks for watching. And Moo Moo Math uploads a new math and science video every day. Please subscribe and share.
Okay, now on to Tectonic Manifesto concept number 3. We can learn a lot about a silicate body's tectonics by studying its surface. So tectonics is expressed on the surface of a thermally evolving body, with that evolution taking place both by mantle convection and by conductive and volcanism-induced cooling. So volcanic activity is a style of convection. Let's ask a question here. Is volcanic activity a style of convection, conduction, or radiation?
Convection.
Yes, I agree, because there's actual physical movement of the material to the surface, bringing heat to the surface. Everybody understand that? Okay, good. How can we tell if a silicate body is tectonically dead or alive? So look at its surface. If it's covered with impact craters, it's dead. If it's covered with basalt flows and cut by faults and folds, it's alive. So for this, I invented the Tectonic Activity Index, and you get 1 point for young volcanism, 1 point for young faulting, and 1 point for very few impact craters. So this is Tectonic Activity Index. TAI is equal to 2 or 3. It's probably active. TAI less than 2, it's probably dead. So this can be resolved just from flying a spacecraft past a planetoid and looking at its surface. We'll talk more about that. So the Tectonic Activity Index ranges from 0 to 3, 1 point each for volcanism. We already covered this. So meteorite impacts, these leave craters. So this is a good example of what happens when a small meteorite hits a silicate planet. This is in Arizona, Barringer Crater, also known as Meteorite Crater. It formed about 50,000 years ago by an iron meteorite about 30 to 50 meters across. That crater is 1,200 meters in diameter and 200 meters deep. And we got about 190 of them that have been identified on Earth. Many, many more have been buried or removed by erosion, which is expected on a tectonically active planet like Earth. This is a map of the 190 impact craters. They're various sizes, and they're for different ages. Silicate bodies are densely cratered because there's nothing to resurface them. Here we got the craters in the moon, and where that surface has been stable for so long that the craters have craters. That just tells you that it just, as we can say, saturated with impact craters. If you have another impact, it's going to cover over an impact. Most of the impacts, especially the large ones, happened early in the solar system history. So this is the cratering rate relative to present versus time. These are billions of years. We're here. And so right now in the solar system, most of the impacts have happened, and it's very rare that you get a major impact. Whereas in the early solar system, you had an incredible impact rate, And the result is something like the lunar surface that is completely saturated with impact craters. Here is Venus. This is a radar image. We can't actually see the surface of Venus visibly because of its dense cloud cover, but we can and have imaged it with radar. So color here corresponds to elevation and roughness. Blues are lower regions. Reds and whites are higher regions. And you'll notice a lack of impact craters because the surface of Venus has been resurfaced by lava. It has a tectonic activity index of 3. You can see quite a few volcanoes up here. You can see lots of tectonic activity, young faulting here. And you can see relatively few impact craters. So it gets a tectonic activity index of 3. It's tectonically quite active. We'll make this point, though, that it does not have plate tectonics. So these are the 7 silicate planetoids of the solar system, the 4 active ones and the 3 dead ones, and their tectonic activity indices. Tectonic manifesto concept number 4. Most silicate bodies cool down with time. With time, most silicate bodies cool down, although some could conceivably heat up, depending on the ratio of surface heat loss to internal heat production by various causes, including radioactive decay, the latent heat of core crystallization, and tidal dissipation. This ratio of internal heat production to surface heat loss is called the Urey ratio. Urey was a very famous scientist, and this ratio of internal heat production to surface heat loss is the Urey ratio. When the Urey ratio is less than 1, the body will cool down with time. When Urey ratio is greater than 1, the body will warm up with time. By most estimates, Earth's Urey ratio is about 0.3. Its interior is cooling down. Okay? All silicate planets were hot at first. So when the solar system began about 4.56 billion years ago, it's easy to remember that time because it's 4.56. The silicate planets and moons were probably molten at first due to several heat sources: the heat of accretion, the heat of core formation, the decay of radionuclides, and intense heat from the beginning of nuclear fusion in the sun's core. So these silicate bodies had magma oceans from which a primitive silicate crust formed. This is a artist's depiction of the magma ocean, and Earth had a magma ocean, it's believed. The outer silicate parts were melted for 4 reasons. One was the formation of Earth's core, and the sinking of iron droplets in the accreted Earth to form the core released energy that heated the body up. It's thought that just the energy of core formation was enough to melt the entire planet. Size is a life or death matter for a silicate planet. So these very small bodies with diameters less than 1,000 kilometers or so, they die tectonically after a few million years. Also, these smaller bodies are never spherical. They don't have the gravity to pull themselves together into a sphere. These are heavily cratered because they've been dead for so long. For example, for the asteroid 4 Vesta, which we mentioned before, has a TIA of 0. Smaller bodies like the Moon and Mercury with diameters of less than 5,000 kilometers tectonically die after a few billion years. And you'll notice we're using GA as shorthand for billion years. These are heavily cratered, so the Moon and Mercury. Intermediate-sized bodies, for example, with diameters between 5,000 and 10,000 kilometers, die after a few billion years. And these are variably cratered. So an example, Mars, is kind of half and half. Large bodies with densities greater than 10,000 kilometers remain active for at least 4.5 billion years, and these are sparsely cratered. For example, Venus and the Earth, which both have tectonic activity indexes of 3. So what do we mean by death? We mean cessation of mantle convection, cessation of tectonics, and cessation of magmatic activity. So here's a good example of a dead body, small dead body. This is 4 Vesta, which was imaged by the Dawn spacecraft 13 years ago. And this is a source of some meteorites we don't have to go into, but we've got examples of them in the Meteorite Education and Research Lab. You're welcome to look at sometime. So there's an example of a fragment of mafic rock from Vesta, which we have. All right. Tectonic Manifesto concept number 5. Tectonic style will change with time as the body cools. So on a tectonically active body with a Urey ratio of less than 1, the lithosphere responds to cooling by thickening, strengthening, and becoming denser with time. So we're talking about most silicate bodies have a Urey ratio of less than 1, so they cool down with time. And the lithosphere responds to that by this cooling by getting thicker, stronger, and becoming denser. And we'll talk about that later. On a silicate body with the Urey ratio greater than 1, which we don't know of any, but it's theoretically possible, the interior, as it warms up, will cause the lithosphere to get warmer, thinner, weaker, and become less dense with time. But because of these changes, the tectonic style of an active silicate body is likely to change with time. This is something to keep in mind when we talk about the origin and the evolution of plate tectonics at the end of the class. Because the mantle cools and the lithosphere thickens on Earth, the tectonic style of Earth was likely to have changed with time. We have plate tectonics now, and the question is, when did that start? All right, so here we see a cartoon which is illustrating the possible stages in the tectonic evolution of a silicate planet from the beginning to the end. This is early magma ocean. There's no lithosphere whatsoever because it's magma all the way to the surface. Maybe there's solid mantle underneath it. We don't know. And then we have this heat pipe style, which is just crust and then partial melt erupting through it. We'll talk about that when we talk about the Jupiter's moon, Io. And then the lithosphere starts to form. It's originally quite thin and weak, and it will drip, and it will rupture to make rivers. That's perhaps what Venus looks like. And then as the body cools, the lithosphere gets thicker and thicker, and the drips become bigger, and the plumes become bigger and fewer. And then at the end, the entire mantle is lithosphere. There's no convecting mantle. So the moon or Mercury would be a good example. And somewhere in this sequence, it's possible that you can go from some style of single lid to plate tectonics. Okay. We'll see this figure again. Tectonic Manifesto concept number 6. Active silicate bodies will cool and eventually tectonically die. So for active silicate bodies with Urey ratios less than 1, eventually the process of lithospheric thickening and strengthening stops tectonics and the body becomes tectonically dead. This means that mantle convection stops. Tectonic death happens rapidly for small bodies, but large bodies retain more internal heat and will remain tectonically active for longer. For example, the Earth and Venus. Now, the early bodies were heated by more radioactive decay than we have today. So today, the interior of the Earth is being heated by radioactivity from potassium-40, from uranium-235, from uranium-238, and thorium-232. These are all radioactive. At the beginning, there was much more of all of these, so that, today our heat flow is on the order of 20 terawatts total, just due to radioactive decay. But back when the Earth formed, it was probably closer to 120. And there were other very short-lived radioisotopes that contributed to heating. Now, this is Earth's cooling history as best we can reconstruct it. So today, we can talk about the mantle potential temperature. The mantle has different temperatures at different depths, but if we brought the mantle to the surface, that would be its potential temperature. And today, the mantle potential temperature of Earth is about 1,350 degrees. In the past, we can reconstruct this by looking at the composition of basalts through time, and also an unusual group of igneous rocks called komatiites. And we can see that back in the Archean, 2.5 to 4 billion years ago, the Earth's mantle potential temperature was more like 15 or 1600 degrees centigrade rather than the 1350 that it is today. And then back at the very beginning, we have the magma ocean, which existed when the Earth's mantle's potential temperature was on the order of 1800 degrees centigrade. So we can see that the Earth is cooling as we would expect because it has a relatively low Curie ratio. All right, so the most important control on tectonic activity is planetary mass. So that's because planetary mass controls cooling. You know, those bodies with less than 5 times 10 to the 23 kilograms mass are dead, and those that are greater are active. So we can look at all of these silicate bodies, Io, Moon, Mercury, Mars, Venus, Earth. Look at their diameters. We've already talked about the importance of diameter, but the mass, look at the differences in mass. So 5 times 10 to the 23, right in there. So all of these ones are active. But here's Io. Io is a very small body and it's very active. Why? What's with Io? It's very small but very active. Okay, this is Io. This is Jupiter. That's Io's shadow. So Io is the innermost moon of Jupiter. It has 400 active volcanoes. It's geologically most active object in the solar system. And this intense volcanism reflects the heating of Io's interior due to tides, solid tides caused by Jupiter and 3 other satellites, Europa, Ganymede, and Callisto. This tidal flexing of Io is like, squeezing and releasing a tennis ball. It heats it up. This kind of deformation, you can get a sense of it by bending a piece of metal over and over again, and eventually the bend will get warm. That's what's happening here. It's tidal flexing of
Hey,
Io.
Bob.
Yes. Yeah.
Question, Eo's composition. I wonder what does that have to do with it, considering it's got a lot of sulfur in it,
Yes.
lighter elements. I just
Yes.
wonder if the melting temperatures, different things like that.
Definitely will. I don't know exactly how much, but that's not the big effect. If Io wasn't that close to Jupiter, it would have long been dead. It would be as dead as the moon. But it's this tidal flexuring that is responsible. Good question, though. Too bad I don't have a good answer for you. All right, so here's what's happening. So this is not a magma ocean because what we've got here this is a basaltic crust. And underneath the basaltic crust, it's imagined there's a zone of large degrees of melting. And every once in a while, one of these will break out and erupt. And that will make more basalt flow on top. And eventually these basalt flows get buried and they're taken down slowly over hundreds or thousands or tens of thousands of years down in the region where it's hotter, and it will remelt and recycle like this. This is called heat pipe. Okay. So mantle convection is tectonic concept number 7. Mantle convection is an important control on tectonics. Mantle convection is caused by differences in density and hence buoyancy. Cooler, denser materials sink, and warmer, less dense materials rise. Risings and sinkings are dominated by the ups and down movement of upwelling plumes and downwelling drips and drapes. Mantle convection mostly happens below the lithosphere, but the sinking of lithosphere in subduction zones drives mantle convection on our planet and any other planet that has plate tectonics, of which we know of none. Mantle convection and tectonics affect each other, but they are not synonyms. That's an important point we'll return to again and again. Tectonic Manifesto Concept 8. Active silicate bodies show emergent behavior. So, emergence is a concept that I'm particularly interested in, which is saying that anytime you have a high energy, far from equilibrium system, it will evolve in ways that cannot be predicted. So mantle convection is a high energy, far from equilibrium system that is farthest from equilibrium in the region of highest temperature gradient, the lithosphere. Such high temperature, far from equilibrium systems are likely to show self-organized emergent behavior that is likely to change with time, unless the Urey ratio is exactly 1, so that the planetoid never cools or heats up, which is almost unimaginable that anybody would have a Urey ratio of exactly 1. The tectonic style of an active silicate body will change with time as the convecting mantle slowly cools and the lithosphere thickens and strengthens. Earth is the only silicate body for which we have a record of how its tectonic style will change with time. And as you'll see at the end of the class, there is no consensus on its tectonic history. The specifics of how emergent systems, like a planet's tectonic style, will change in the future cannot be predicted. Well, let's watch this.
The concept of emergent phenomenon explains that any high-energy, far from equilibrium system will organize itself in ways that cannot be predicted from knowing its individual components. In a nutshell, an emergent system will organize itself so that energy flows in the system will be less chaotic. Emergence is not a theory. It is a way of looking at many different kinds of energetic systems. Emergence is closely related to self-organization, complexity, and evolution. Many things exhibit emergent behavior. Animals, ecosystems, oceanic currents, hurricanes and spiral galaxies, hydrothermal systems, and civilizations are just a few examples. In emergent systems, low-level rules for constituent parts give rise to higher-level system complexity. Entirely new properties and behaviors emerge, without direction and with characteristics that cannot be predicted from knowledge of the constituents alone. In the January issue of GSA Today, Bob Stern of UT Dallas and Taras Gurria of ETH Zurich discuss how thinking about emergence can help us gain new perspectives about Earth history. In this short groundwork article, they discuss how thinking about emergence can help us understand Earth and other silicate planets and moons and how their tectonics evolved. Convecting silicate planets are high-energy, far from equilibrium systems, and as their interiors cool, their lithospheres respond by becoming thicker, denser, and stronger. On Earth, these tectonic styles are likely to have merged into the plate tectonic system we see today. Want to learn more? Check out Earth evolution, emergence, and uniformitarianism in the link provided below.
All right, Tectonic Manifesto Concept 9. Interactions of deeper mantle convection and lithospheric determines an active silicate body's tectonic style. The tectonic style of an active silicate planet mostly mirrors convective behavior. The interaction between convecting mantle underlying the lithosphere and the lithospheric response determines an active silicate body's tectonic style. Tectonic Manifesto Concept 10. Mantle plumes are features of all tectonically active silicate bodies. Mantle plumes, which we'll talk about more in this class, these are sites where warm, buoyant mantle rises in the mantle and reaches the crust and erupts. These reflect thermal chemical instabilities in solid mantle. Tectonically active silicate bodies beyond the magma ocean will have mantle plumes. When I say beyond, I mean after the lithosphere begins to form. Mantle plume activity correlates with other indicators of magmatotectonic activity. And the number of mantle plumes can help distinguish between tectonically vigorous silicate bodies with many, sluggish bodies with few, and dead bodies with none. So here's plume-related volcanism on Mars. This is Olympus Mons, the largest volcano in the solar system. You know, just this caldera is 80 kilometers across. The entire volcano is 625 kilometers across and 25 kilometers high. It's a monster. Mars has, let's see, there's many plumes on Venus as well. So this is sort of a reconstruction of what the Venusian mantle plume situation is. And over here, you're looking at temperature versus the melting temperature of material. We would call that the geotherm on Earth. But since this is Venus, we can call it the venotherm. And you own this temperature profile intersects what we call the solidus, which separates the realm of pure solid material from that where there's partial melt. It's only at the very top of the ascent of these mantle plumes that you begin to get partial melting to make the volcanoes. And on Venus, you have mantle plumes, you have regions where there's compressional tectonics, and there's regions where you have extensional tectonics, but no plate tectonics. Another good example is the Hawaiian Islands. These are the Hawaiian Islands. Clint can show you some nice pictures he took recently. There's the Big Island where the mantle plume is presently. The Pacific plate is moving this way. And so these islands get older and older as you go farther away from where the plume is now. The oldest ones here, Kauai and Ni'au, are only 4.5 or 4 or 5 million years old. These islands are the surface expression of the Hawaiian mantle plume. So what's going on beneath Hawaii? This is the idea. If we take a section here, A prime, and look what's going on, it seems that there's two upwellings, one to cause this trend of volcanism and the other one to trend this one. And it's argued that these mantle plumes start at the base of the mantle, where we have the core mantle boundary is getting heated up by the core, and that's causing the thermal instability that's causing these volcanoes. Watch video.
The people here might not be quite so relaxed if they knew exactly how the water gets heated. Just 12 miles beneath Iceland is a vast column of superheated rock called a plume. It's over 100 miles wide and at least 370 miles deep. Created more than 50 million years ago, the plume is sustained by heat continually rising up from Earth's hot core. This giant plume does more than just warm up Iceland's hot springs. It also created Iceland itself. In 1963, there was an event that showed how it might have happened. A volcano just below the sea's surface blasted its way out of the water. A new island, Surtsey, was born. This is what Iceland must have looked like more than 50 million years ago when it first burst above the surface.
So plate tectonics versus single lid tectonics. Based on the presence or absence of a global, connected, mobile mosaic of rigid plates separated by narrow, high-strain plate boundaries, we classify tectonics into A, plate tectonics, like the modern Earth, and B, single lid tectonics, other active silicate planets and moons. The latter can be further subdivided into four main subtypes, characteristic of different planetary bodies, depending on their size and interior temperature. From most active to dead, these are B1, volcanic heat pipe, small bodies with partially molten interior, B2, squishy lid, single lid bodies, large bodies with hot interiors such as Venus, B3, sluggish single lid, with few large drips and plumes like Mars, and B4, stagnant lid, small bodies with cold interiors like Mercury, the Moon, and Vesta, the tectonic and dead ones. All right. Tectonic Manifesto Concept 11A. Plate tectonics is a global tectonic system whereby the lithosphere is divided into a global mosaic of strong plates which move on and sink into the weaker ductile asthenosphere. Three types of localized plate boundaries form the interconnected global network. New oceanic lithosphere is created by seafloor spreading at mid-ocean ridges. We'll talk about that. Old oceanic lithosphere sinks at subduction zones. We'll talk about that. And two plates slide past each other along transform faults. We'll talk about that. The negative buoyancy of old dense oceanic lithosphere, which sinks in subduction zones, mostly powers plate motions. Most people have been taught that mantle convection is responsible for moving the plates. That is not correct, as you will learn in this class. So, this is another paper that I wrote with my colleagues at ETH in Switzerland on single lid tectonics. I think that's in, I've added in e-learning, right now there is the syllabus, there are a few of the PowerPoints as PDFs, including this one, and a folder called For Those Who Want to Learn More, which has the readings that are called out in the syllabus, plus a few others. This is in there. Okay, Tectonic Manifesto Concept 11B. Some use the term mobile lid as a synonym for plate tectonics. Plate tectonics is a type of mobile lid tectonics, but with a clear driver of plate motion due to the sinking of dense lithosphere in subduction zones. The term mobile lid tectonics implies that there are other drivers of plate motion on active silicate bodies. If other drivers of plate motion exist, they are not yet clearly articulated, so we do not prefer this term. So these are mobile lids of Enceladus, Enceladus, which is Saturn's moon, and Europa on the right, which is Jupiter's moon. These may be mobile fragmented lids, but cannot be plate tectonics because these are icy bodies, and ice does not have um, the physical properties of silicates to allow plate tectonics. Tectonic Manifesto Concept 11C, single lid tectonics, embracing but not limited to volcanic heat pipe, squishy lid, sluggish single lid, and stagnant lid, contrasts with plate tectonics in that there is no global mosaic of moving rigid tectonic plates divided by weak tectonic boundaries, and or there is no long-lived subduction that drives sustained horizontal plate motions like there is on Earth. Tectonic Manifesto Concept 11D, the strict distinction of single lid and plate tectonics advocated here is proposed to discriminate modern Earth tectonics from Venus tectonics, in which short-lived subduction zones are triggered by mantle plumes and regional scales horizontal surface motions are caused by mantle convection currents. These are things called corona, and I hope we have time in the next lecture to go into them. These are unique features to Venus that are worth talking about. You can see the scale bars here, and these are the distribution of fossil corona and ones that are still active in red. So this is an example of what happens around these corona. This is a mantle plume rising up, rupturing the lithosphere. In some places, it causes the surrounding region to bend down and deform. There are occasional subduction zones that last briefly and do not interconnect. And so there could be local subduction around some of these Venusian corona, but there is no global mosaic and thus no plate tectonics. Tectonic Manifesto Concept 11E. Prolonged transitions in tectonic styles must occur between single lid and plate tectonics. So here we're looking at Earth history for the last 2.5 billion years. We're over here today. This is plate tectonics in blue. And these are the tectonic episodes that I have articulated in my most recent paper in GSA Today, which is will be available in hard copy in the near future. But I can give you, if you want to see it, I have PDFs of it. And these are Clint's sketches. He really helped me a lot by making them. So what we can see here is my interpretation of Earth's last 2.5 billion years of Earth tectonic history. We're currently in plate tectonics episode and have been for on the order of 800 million years. And during the Mesoproterozoic, it was a single lid episode, and there was a transition between them. And before that, there was another plate tectonics episode between about 2.1 and 1.8 billion years ago. Before that, there was a single lid episode. Before that, we're getting to the Archean, which I really don't understand that tectonics style yet. This is my interpretation of the last 2.5 billion years of Earth's tectonic history. Most geoscientists disagree with me. Useful information for you. Tectonic Manifesto Concept 12. Changes in tectonic style will affect other planetary systems. Because it is an emergent system, the tectonic style of an active silicate body is likely to change through time. For example, from one style of single lid behavior to another, and from single lid to plate tectonics, or vice versa. Tectonic transitions are likely to take many millions of years to accomplish and may profoundly disturb the surface environment, the composition of the atmosphere, the body's rotational axis, and many other planetary characteristics. So I'm going to stop there. We haven't quite gotten through the Tectonic Manifesto, but I hope you sort of see some overarching principles that we can use in our exploration of plate tectonics in the rest of the class. And I'll continue this lecture on Wednesday.